understanding variation is mostly getting used to the language around it and then dealing with fractions and proportions and things of that sort. So a lot of what I'm going to be saying, it's going to be mostly words today rather than a lot of equations. And if you get behind on your note-taking, please feel free to go, on Moodle to get the lecture notes here and the recording. There will be a lot to write if you're going to keep up. So just, kind of make yourself a side note if you don't want to, write the whole thing out. But anyway, when we talk about direct variation, we can say that in several different ways. We can say y is directly proportional to x. That's what direct variation means. That's what direct variation, how it's stated. Or equivalently, we can use a formula. We can use a formula y equals kx for some constant k. So if we know x and we know k, then we can calculate what y is. So it's a very simple kind of equation. Another way it's sometimes stated is that y varies directly as x. Okay, so when you say that y varies directly at x, you know that there's a constant k that kind of defines the relationship between the two of those. Okay, so an example is cost. Cost is directly proportional to quantity. Now, an example of this would be 5 units cost $30. How much does 7 units cost? All right, well, you can figure out if you're just doing this informally, the price of this thing is 5 units cost $30. That means they're $6 a piece, and so 7 of them will cost $42. That's one way to do it. The way to do it that I'm talking about here with variation is that since cost is directly proportional to quantity, we'll set up our proportion here, or our relationship, where we have C as the cost, N as the quantity, and we have this constant that is C divided by N, because I'm solving for K at the beginning, and then I'm going to use this constant to multiply by the new quantity to get my new value. So 30 over 5 is the cost of 30 for 5 units, and so some cost for 7 units, we calculate that by just multiplying 7 times 30 divided by 5 and get 42. So no earth-shattering things here. This is just basically a proportion rather than calculating the price and then going from there. So it's really more the language, the words that I use than the actual calculation that should be new. Okay, so another example would be a spring. An ideal spring follows what's called Hooke's law. The force is proportional to the distance that it's stretched. Okay, and you kind of know that intuitively. You take a spring, you stretch it, take some force, you stretch it some more, and it takes even more force, right? Or a lot of scales operate this way. A hanging scale that you'll see in the grocery store is on a spring, so the more produce you put in there, the lower the basket goes, and the pointer will tell you, how much weight you have. So that follows Hooke's law. So if we were to, let's say, have a spring, let's say a force of 50 pounds stretches a certain spring 3 inches. How much will 20 pounds stretch the spring? Okay, that's one question. Another question could be something like, how much will the spring stretch, or how much weight will stretch the spring 4 inches? So we can go both ways on this. This isn't just necessarily a one-way relationship. We have this constant that we're dealing with. Okay, so our proportionality relationship here is that the distance the spring stretches is some constant times the force. That's what Hooke's law is all about. And then when I put in my numbers, I know that for a force of 50 pounds, it stretches at 3 inches. So I can calculate K directly from there. And really, not simplifying it beyond here is just fine, because you don't want to deal with decimals quite at this point. So now that we have K, we can figure, okay, 20 pounds, so 20 times K will be the distance that it stretches, or 6/5 of an inch. 1.2 inches. The second question would be, all right, so we'll take the distance that it goes 4 inches divided by k, and so we get 4 times the reciprocal of k, 50 over 3, and that's 200 divided by 3, which is 66.7 pounds. And that's what you would expect, right? If 50 pounds stretches at 3 inches, it would be reasonable to think that 66 pounds would stretch it somewhat more, which is 4 inches. Okay, so things not only vary proportionally, they vary sometimes proportionally with an nth power of a variable. So this would be stated, if you were to read something like this, it would say something like y varies directly with the nth power of x. Okay, so if n is 2, then y varies directly with a second power of x. So we have these kinds of things going on. Another way to say that is y is directly proportional to the nth power of x. Okay, so those are, you know, interchangeable. One says varies directly, the other one is directly proportional, and they mean the same thing. And then if we want to see it in an equation, it would be y equals kx to the n for some constant k. So the key thing here to remember is that k is constant. You may or may not know k, but you can do a lot of manipulation just knowing about this relationship. Okay, so when does this arise? Some examples of this kind of stuff. Nth power variation. We have, you know, area versus a linear dimension. Like the formula for the area of a circle is area equals pi r squared. And in this case, k is actually pi, right? K is that constant, the proportionality constant. So we say that the area varies with the square of the radius, all right? So it's not even important if we're trying to compare areas, it's not even important to know what pi is, but just to understand that relationship. Another instance would be if we're talking about volumes in terms of linear dimensions. The volume of a sphere is 4/3 pi r cubed, and so you would say the volume of a sphere varies with the third power of the radius. And constant acceleration versus time, the distance is equal to some constant times time squared. This is what happens when you're in a gravity field, because gravity causes a constant acceleration, and so the distance that you go when you're falling, you fall faster and faster and faster, so you go a further and further distance with longer and longer times. And it's not just proportional. We'll see in one example that it actually increases quite a bit. Okay, so let me take an example here. If the area of a circle varies with the second power of the radius, that's what I showed you before, a equals pi r squared. Okay, if a circle's radius is increased by 60%, I forgot my apostrophe there on circles, but if it's increased by 60%, what happens to the area? All right, well, we don't know the radius, we don't know the area, but we increase the radius by 60%. We can know how much the area increases by using these proportionality, these variation relationships. So the basic one is that the area is some constant times the radius squared. And so if we first solve for k, we have a divided by r squared is k. And we can come up with a relationship here that says that a sub 1 means the area of one circle divided by the radius squared of that circle is equal to the area of the second circle divided by the radius of the second circle squared. So we have this relationship. Notice I'm not going to ever get to the value of k here. I'm going to just use the fact that this a versus r squared stays constant. All right, so we'll do a little manipulation here. I'm going to change this equation, multiply both sides by r squared, r2 squared, and so I get this thing up here. And then I'm going to note that since I increased my radius by 60%, the new radius is going to be 1.6 times the first radius, right? It's not 0.6, that would make it smaller. It would be 1.6 because you have the original radius plus 60% more. Then I'll make the substitution, 1.6 r1 squared, and when I take 1.6 squared, I get 2.56. And notice now I have R1 squared both in the numerator and the denominator, so that will cancel out. And this tells me then that if I increase my radius by 60%, my radius increases by how much in percent? So the second area is 2.56 times the first area. So in a percent increase, how much is that?
250.6?
Hmm?
250.6.
No. How about 156%? Okay, because if it was 1, it didn't increase or decrease, right? It would be 100% of the size. But since it's going up to 256%, it's increasing by 156%. Okay, does that make sense? Just like I added the 1 to get to this 1.6 from the 60%, I'm going to subtract 1 to get my 156%. So this is kind of remarkable when you think about it. You know, you increase the circle's radius by 60%, and you over double the area. Okay, so here's one. I'd like you to try this. A ball rolls down an incline, and the distance it rolls is directly proportional to the square of the time it rolls. Okay, so there's my key statement. The distance it rolls is directly proportional to the square of the time it rolls. During the first second, it rolls 6 feet. How far does it roll? And I should have said here the first 2 seconds. It's not 2 additional seconds, but if I'm timing it from the beginning, at 2 seconds, where do I expect that thing to be? If at 1 second, it's at 6 feet. And there I actually lay out the variation relationship directly for you. What do you think? How far does it roll? I think I heard it. Somebody say something? Yes. 24 feet. Okay, so how did you get that?
You set it up so that 6 equals k times 1 squared,
Yeah?
and then you have k equals 6, and then you plug it into the equation of the distance, and you have distance equals 6 times parentheses 2 squared, and that's
6 times 4 is 24 then. Great. Okay. Everybody see that? All right. Now we're going to talk about different kinds of variation, and the first one here is inverse variation. And so y varies inversely as x. Okay, you might see a statement like that. Or you might see a statement that says y is inversely proportional to x. And so what this means from an equation standpoint is that y equals k over x. Okay, so notice that in this case that when x increases, y is going to decrease, and vice versa. When y decreases, X is going to increase. Now we also can say it's inversely proportional to the nth power of X. Okay, and we're not going to deal with this one too much, but that's what that means, is that when you say it's inversely proportional, we're talking about a reciprocal relationship, and then you can make it an nth power. All right, can I go on? Is everybody just about done writing? I know it's a lot to write. Okay, so let me give an example of that. Okay, so the sales of a product is inversely proportional to its price. Okay, so you might hear a statement like that. And so if you think about what it means, the sales of a product is inversely proportional to its price, you would expect that as the price increases, sales go down. As the price decreases, sales go up. Okay, and that's what the inversely proportional means. So if at $5 a unit, sales are at 10,000 units, how many are sold at $4 a unit if you have this relationship holding? Okay, so what we do is we set up our basic relationship where y is k over x, define our variables, y is the units sold, x is the price. And so we have 10,000 equals k over 5, where k equals 50,000. So k is our proportionality constant. And so then we can plug in 50,000 divided by 4 is 12,500 units. So you'd expect 12,500 units to be sold at $4 if this relationship holds. Now in reality, the markets don't work so cleanly, but it's a simple example. Okay, so here's one for you. Travel time is inversely proportional to speed, right? The faster you go, the shorter time it takes you to get there. The slower you go, the longer the time. So at 50 miles per hour, a trip takes 3 hours. How long will it take at 60 miles per hour? Now, of course, you can calculate the distance off this and use the rate times time equals distance thing, which really amounts to about the same formula that you're going to come up with here. But I'd like you to do this as an inversely proportional ratio rather than just calculating the miles. Okay, so once you set up these proportions then, y equals k over x, you can note by the units of everything that k is actually your distance that you're traveling. And so when you have a simple relationship like rate times time equals distance, you do get some meaningful values for your k occasionally. And we'll see one case where the k really is too complicated to try and understand it. But here we have 150 divided by 60 is going to be, now how do you reduce that? You factor it, cancel terms, you get 5 over 2, which is going to be 2.5 hours. Okay, so you speed up, takes you less time, so that works. So now we have the last kind of variation. We call this joint variation. And joint variation means that you have more than one variable. Like probably if you remember from chemistry, the ideal gas law is PV equals nRT. So you would say that the temperature varies jointly with the pressure and with the volume. Okay, so there's an example where you have more than one variable. You can say Z is jointly proportional to X and Y. And the way it looks in an equation is Z equals KXY for some constant K. So here you can have more than one factor involved and you get something. So if I show you an example here, we'll talk about interest. Interest is jointly proportional to the time and principal. Okay? So if you make $100 in interest on $5,000 saved for 4 months, how much will you make on $4,000 saved for 6 months? Okay, so one of the strategies you can use to solve this problem is that you can figure out what your interest rate is and then reconstruct a simple interest formula. Or we can just use the fact that the interest is jointly proportional, so we have our relationship Z equals KXY. Z is interest, X is the principal, Y is the time. And so we can solve for K. K is 100 divided by 5,000 times 4, which is 1 over 200. Now, whatever the physical meaning of 1 over 200 is, it's not important because we can just take that as our proportionality constant and take 1 over 200 times 4,000 times 6, and we get $120. So I never did actually compute the interest rate. That wasn't the question. I was just looking for a different time frame and a different saved amount. So I get something that is a little different. The savings went down, so you'll expect less interest from that, but the time went up, so you expect more interest from that. Turns out you're making a little bit more by doing this. All right, everybody up with me on notes here, or you want me to give you another second? Okay, we good? Okay, so here's one for you. So the volume of a gas, so this is kind of using the principle of the ideal gas law, but we're not going to use that directly because I don't want to noodle with R. Remember, R is that strange value that has weird units and all that. But I'm just going to say, okay, the volume of a gas varies inversely as the pressure P on it. Okay, we know PV equals nRT, so P times V equals some constant because we're not changing the temperature or the amount of gas that we have. So if we divide both sides by V, we get P is inversely proportional to, or V is inversely proportional to P. All right, so if the volume is 200 cubic centimeters under a pressure of 32 kilograms per square centimeter, what will its volume be under a pressure of 20 kilograms per square centimeter? So we calculate K as 6,400, and then we put that back in our original equation, 6,400, and our new pressure is 20, so we take 6,400 over 20. Is that what you said?
Yeah.
320? I'm sorry, I was thinking
okay.
32, but now that I see that, I think, yeah, you're right, Maddie. Completely right. So I'm sorry. Okay, so we get 320 cubic centimeters. Okay, so now does everybody get that? Do you follow that? I know sometimes starting doing the examples in class can be a little tricky, but I'd like you to try it, though. Okay,